In this video, we will be going over linear approximations. If we zoom in on a smooth curve near a point, the curve begins to look like a straight line. We can use this line, the tangent line, to estimate nearby values. The formula for the linear approximation or linearization of f of x at x equals a is L of x equals f of a plus f prime of a times x minus a. This is a variation of point slope form. So as we know, point slope form looks like this: y minus y1 equals m parentheses x minus x1. And if I just solve this for y and move this over, you can see that we're basically just mirroring that format over here. So here's how this helps us. If we want to look at this first example, let's say we want to estimate the value of radical 5. So just thinking logically, we could probably guess that the value is between 2 and 3, because we know that square root of 5 is somewhere between square root of 4 and square root of 9, right? Those are two perfect squares, 4 and 9. So we know that since those values are 2 and 3, radical 5 has to be somewhere between 2 and 3. But we want to come up with more of an accurate estimate, and we can use linearization, or again, the method of linear approximation, to do that. Okay. So first, let's think about what function we're referring to here. So we're looking at the function f of x equals square root of x. And we want to pick a value that's close to 5, something that we can work with comfortably and actually get an answer. So before I talked about the idea of using 4 and 9 as a way to help us estimate, I'm going to use the value of 4 in this example since that is closer to 5. So I'm going to make a equal 4 in this problem. Now what we're going to do is we're going to fill in basically all of the missing pieces. We know that if a is 4, that basically our output would be 2, right, if I plug that into the function. But what about the derivative part? So if I find the derivative of square root of x, that's going to give me 1 over 2 radical x. And if I find that value, let's actually sub in here. If I find that value at 4, I'm getting 1 over 4 basically as our slope of the tangent line. So let's kind of put this together. Let's write it in point slope format so we can make some sense of it. So of course, to use point slope formula, we need a point and we need a slope, and we have those two things, right? So here's our point, 4, 2, and here's our slope, 1/4. And basically what this is going to do is write the equation of the tangent line. So over on the left, if you look at the picture, we're trying to estimate what's happening at 4 here. So we are writing the equation of the tangent line at 4, and you can see if I zoom in here, over at 5, the tangent line and the curve are very, very close to one another. So that's how we're coming up with an estimate, okay? So we're coming up with something closer than saying, oh, it's between 2 and 3. We're using this tangent line to help us get a better idea. Okay. So let's plug all these pieces in. So I have y minus 2 equals 1/4 x minus 4. And we could bring that 2 over like we saw in the formula at the top. And that's basically our equation of L of x, right? That's basically our linear approximation equation. And now we want to use this to evaluate 5. So if I plug 5 in here, I would get 2 plus 1/4 times 1, or 2 plus 1/4, or 2.25. So that is our more accurate guess of what radical 5 is equal to. Now, over on the side here, you can see that I put the actual value as 2.2360 and so on. So you can see that we have a slight overestimate here. Okay? So our linear approximations will always be overestimates or underestimates. And we said basically that this was an overestimate. And the reason this is happening is, yes, because we can compare 2.25 to 2.23 and say, oh yeah, that's bigger. But also if we look at the graph, and I zoom back in over here, if I look at the tangent line, I can see that it's above the curve, right? So anytime the tangent line is above the curve, and this is going to happen anytime our graph is concave down, that's when we are going to get an overestimate. So let's summarize that at the bottom. So it says here that a linear approximation is an overestimate, and that's going to say when the function is concave down. And remember what concave down looks like, kind of like an upside down U. Okay, something like that. And it's an underestimate, therefore the opposite when the function is concave up, which looks like an upward facing U. Okay, so again, basically the equation of a tangent line helps us better estimate values. And we just have to acknowledge that, of course, our estimations are simply that. They're an approximate value. So we have to then determine, is it going to be an overestimate or an underestimate? Okay. Let's look at a couple more example problems. So number 1 says, use linear approximation to estimate the value of e to the 0.1. Okay. I don't know what the value of e to the 0.1 is, but I know what the value of e to the 0 is. So I want you to think when you see a problem like, well, what do I know? I know e to the 0 is 1. Okay, so I can maybe guess that this answer is going to be a little bit greater than 1. And we want to use that type of reasoning. But then we want to put it all together and actually use the linearization process. So I'm going to say, well, our function that we're looking at here is f of x equals e to the x. And we're going to say in this case that a is 0. Okay. We said just now that 0 would produce an output of 1. If I find the derivative, I have the derivative e to the x is itself. And if I find the derivative at 0, I'm going to get 1. So remember to use point-slope form. You need a point, which I have. You need a slope, which I have. And we're going to put that all together. So y minus 1 equals 1, x minus 0. We can clean this one up a lot. And we get y equals 1 plus x or x plus 1. You could write it either way. And that is, again, our linearization equation. Now what we want to do is actually plug in the value that we're trying to estimate. So I'm going to say that we are trying to find the output when we are plugging in 0.1. So 1 plus 0.1 is 1.1, and that would be our final answer to this question. For part B, we wanted to determine if our answer was an over approximation or under approximation. Well, we should know e to the x is concave up and looks something like that. So when we draw a tangent line, it's going to be slightly below the curve. So this is an under approximation or an underestimate. So for this example, along with the one that was on the first page earlier in the video, we basically want to figure out what function we're talking about and then find all of the missing pieces. We want to reemphasize the idea that equation of a tangent line requires us to know point and a slope so we can plug that into point-slope form. All right, let's look at another one that's stylized a little bit different here. So number 2 says let f of x equals negative x squared plus 6x. It's telling us that it's concave down at 2, okay? And we know then that therefore we're trying to use 2 in this problem. So before I was guessing, if I just scroll for a second, on number 1a, I was guessing that a was 0 because I was like, okay, well, I know what e to the 0 is. Here they're telling us what value to use, okay? So let's find all of our missing pieces. If the x coordinate is 2, when I plug 2 into f of x, I'm going to get my output as 8. So that's my point. Okay, then I also have to find the slope. So f prime of x would be negative 2x plus 6, but I want to evaluate that at 2. And that's going to give me an output of 2. Let's take a look at what this looks like in point-slope form. So I'll rewrite the formula here. So I have y minus 8 equals 2, parentheses x minus 2. Okay, we can move that 8 over. We could distribute. You have a few options here of what order you do your steps in. But I'm basically getting y equals 2x plus 4. That's our linearization. That's our tangent line, and now I'm going to plug in the value we want, so I'm going to plug in 2.2. Okay, when I do that, I get my answer to be 8.4. So we are again estimating here that the value or the output that corresponds to the input of 12.2 would give us 8.4. Okay. If we were to go to our calculator, we could of course compute the actual value. That would come out to 8.36. So you can see that we have a little bit of an overestimate here. But again, I don't need my calculator to come up with the underestimate or overestimate part, because I know up here it tells me that the graph is concave down. So I'm going to say this is an overestimate because the graph is concave down at x equals 2. And if you want, we could add to it and say, which means the tangent line is above the curve. All right, let's look at one last example. In number 3 here, we are not given a function at all. It says f is concave up and f of 2 equals -1, f prime of 2 equals 3. We want to find the estimate of f of 2.1 using the local linear approximation for f at x equals 2. So when we're taking a look at this here, we are given our point, we are given our slope. So I have all of the pieces that I basically need here. So I'm going to plug in 2-point slope form. Okay, when I solve for y here, I'm going to get y equals 3x minus 7. All right, finally, we're going to plug in the value we're trying to estimate. So plug in 2.1. And when I simplify that, I'm going to get that our approximate value is -0.7. B says, is it an underestimate or overestimate? Well, if we look in the problem, it tells us that f is concave up. So I'm going to say that this is an underestimate. Because f is concave up. So the tangent line is below the curve.